Hi, I'm Swarupa Said, course instructor for Fluid Mechanics. In this presentation, we will go through continuity equation in 3 dimensions. For a flowing fluid through the pipe at every cross section, the quantity of fluid per second will remain same. Consider a pipe through which fluid is flowing. And again, in that, consider an element of having length dx, dy and dz in the direction of x, y and z respectively. Mass of fluid entering the phase A, B, C, D per second is equal to density into velocity in x direction into area of ABCD. So, mass of fluid entering the phase ABCD per second will be equal to density rho into velocity in x direction, that is u, into area of ABCD, which will be dy in this direction and dz. So, length into width. Hence, mass of fluid entering the phase ABCD will be equal to rho u dy dz. Similarly, mass of fluid leaving the phase E, F, G, H per second is equal to rho u dy into dz plus dou by dou x of rho u dy dz of dx. So, gain of mass is equal to mass flow rate into the system minus mass flow rate out of the system. So, gain of mass can be written as mass of fluid entering the phase ABCD per second minus mass of fluid leaving the phase EFGH per second. Hence, we will have the equation for mass gain in x direction as rho u dy dz minus rho u dy dz plus dou by dou x of rho u dy dz of dx. So, gain of mass in x direction will be minus dou by dou x of rho u dx dy dz. Similarly, mass gain in y and z direction can be written as minus dou by dou y of rho v dx dy dz, which is the gain of mass in y direction. Similarly, mass gain in z direction is equal to minus dou by dou z of rho w dx dy dz. Net gain of masses will be equal to minus dou by dou x of rho u plus dou by dou y of rho v plus dou by dou z of rho w of dx dy dz. As per the principle of conservation of mass, mass could not be created or destroyed in the fluid element. Hence, net increase of mass per unit time in the fluid element should be equal to the rate of increase of mass in the fluid element. Mass of fluid in the fluid element is equal to rho dx dy dz. So, rate of increase of mass in the fluid element is equal to dou rho divided by dou t into dx dy dz. Hence, minus dou by dou x of rho u plus dou by dou y of rho v plus dou by dou z of rho w dx dy dz is equal to dou rho divided by dou t into dx dy dz. And we will take out the term dou rho by dou t on the right hand side. So, we get minus dou by dou x of rho u plus dou by dou y of rho v plus dou by dou z of rho w is equal to dou rho divided by dou t. So, dou rho divided by dou t plus dou by dou x of rho u plus dou by dou y of rho v plus dou by dou z of rho w will be equal to 0. So above equation is the continuity equation in Cartesian coordinates in its most general form, and this equation is applicable to following types of fluid flow, that is when the flow is steady and unsteady, and when it is uniform and non-uniform, and even when the flow is compressible or incompressible flow. For steady flow, continuity equation will be mentioned as below. For steady flow, dou rho by dou t will be equal to 0 as change in all the parameters with respect to time is constant. So we get equation as dou by dou x of rho u plus dou by dou y of rho v plus dou by dou z of rho w will be equal to 0, since dou rho by dou t is equal to 0. For incompressible flow, continuity equation will be as mentioned below, that is rho will be constant and we will have following continuity equation: dou u by dou x plus dou v by dou y plus dou w by dou z will be equal to 0. So this is the continuity equation in 3 dimensions. But for 2-dimensional flow, W will be 0 because there won't be any flow considered in third direction. So flow will be considered only along x and y direction. So we get dou u by dou x plus dou v by dou y equal to 0, as dou w by dou z is considered as equal to 0 for 2-dimensional flow. Thank you.